This section covers Hadoop Distributed File System, HDFS. What is Hadoop Distributed File System, HDFS? HDFS is the primary storage system of Hadoop, designed to store very large datasets across multiple machines in a cluster. Key features: distributed storage. Large files are split into blocks, typically 128 megabytes each, and stored across multiple nodes. Fault tolerance. Each block is replicated on multiple nodes, default 3 copies, to prevent data loss. High throughput, optimized for batch processing, rather than low latency access. Scalability, can grow to thousands of nodes in a cluster. Streaming data access, follows a write once, read many pattern for efficient data processing. This slide tells about the HDFS architecture. Step 1, read request from MapReduce. The MapReduce job initiates a request to read data stored in HDFS data blocks through the HDFS client. Step 2, get block location. The HDFS client sends a request to the NameNode asking for the location of the required data blocks. Step 3, NameNode gives location. The NameNode responds by providing metadata, which contains the addresses of the DataNodes where the data blocks are stored. Step 4. Read data from DataNodes. Using the received location details, the HDFS client directly reads the data from multiple DataNodes, number 1, number 2, number 3. Step 5, parallel processing. The data is read in parallel from different DataNodes, allowing MapReduce to process large data efficiently and faster. Components of HDFS. The Hadoop Distributed File System, or HDFS, consists of multiple components that work together to store and process large volumes of data efficiently. MapReduce. This block represents MapReduce. MapReduce processes large datasets in parallel using the map and reduce programming model. It divides computation into smaller tasks and executes them across multiple nodes. This parallel execution improves performance and provides fault tolerance. HDFS client. This block represents the HDFS client. The HDFS client acts as an interface between the user or application and the HDFS system. It requests metadata from the NameNode and reads or writes data directly to DataNodes. The HDFS client does not store data, it only manages communication and file operations. NameNode, master node. This block represents the NameNode, which is the master node of HDFS. The NameNode manages the file system namespace. It stores metadata such as file names, block locations, and access permissions. It directs client requests to the appropriate DataNodes. Since it is a single point of control, high availability mechanisms are used for fault tolerance. DataNodes, worker nodes. These blocks represent the DataNodes, which are the worker nodes of HDFS. DataNodes store the actual data blocks on their local disks. They handle read and write requests directly from clients. DataNodes regularly send heartbeats and block reports to the NameNode to confirm their status. HDFS architecture, working. This slide explains how the HDFS architecture works, step by step, during data processing and execution. Data storage in HDFS. First, large input files are divided into fixed-size blocks. These blocks are distributed across multiple DataNodes in the HDFS cluster. This distribution allows parallel data access and ensures fault tolerance through data replication. Job submission. Next, the user submits a MapReduce job using the HDFS client. The job contains the program logic and specifies the input data to be processed. This request initiates the data processing workflow. Metadata request to NameNode. The HDFS client then contacts the NameNode to request metadata about the input files. The NameNode provides information such as block IDs and the corresponding DataNode locations. Only metadata is shared at this stage, not the actual data. Block location response. The NameNode responds by sending only the block location details to the HDFS client. It does not take part in the actual data transfer. This reduces system overhead and improves scalability. Direct data access. Using the received block locations, the HDFS client directly reads data blocks from the nearest DataNodes. Direct access minimizes network latency and significantly improves performance. Map phase execution. During the map phase, map tasks process the input data blocks in parallel. Each mapper reads data and converts it into intermediate key-value pairs for further processing. Now let's look at the applications of HDFS. First, HDFS is widely used for big data storage. It can reliably store extremely large datasets across distributed clusters. Next, HDFS acts as the storage layer for data analytics platforms such as MapReduce, Spark, and Hive. Third, HDFS is used for log and event data storage, where huge volumes of system logs are collected and analyzed later. Then, it supports data warehousing, allowing organizations to store both structured and unstructured data at scale. Finally, HDFS is used in backup and archival systems, providing a cost-effective solution for long-term data storage. Overall, HDFS enables scalable, reliable, and efficient big data management. Advantages of HDFS. HDFS offers high scalability. It can easily store and process very large datasets by adding more nodes to the cluster. It provides fault tolerance. Data is automatically replicated across multiple nodes, ensuring reliability even if a node fails. HDFS supports high throughput, as it is optimized for large sequential data access. Finally, it ensures reliable storage, keeping data available even during hardware failures. Disadvantages of HDFS. HDFS has high latency, so it is not suitable for real-time applications. It is inefficient for small files, as it works best with large datasets. HDFS follows a write-once, read-many model, which limits frequent updates. Lastly, it has limited interactive access, making it unsuitable for transactional workloads.